on top of bilayer graphene, you will see that there's a significant renormalization of the gap, about 100 milli-electron volt, more than that, and a 25% reduction of the binding energy of the exciton, even though the optical transition energy seems to be hardly changed, and that's because of cancellation effect of both the band gap renormalization and the binding energy of exciton changing. And one could probe this experimentally by doing both a STS experiment, which measures directly the quasi-particle gap, and optical experiment. These are done by Crowley's group and Fan Wong's group at Berkeley, and indeed you see that there is now significant agreement between theory and experiment if you include the substrate effects. Substrate effects are even more dramatic on another popular 2D material, so-called black phosphorus. A monolayer black phosphorus has this structure. People are excited about it because it has a band gap around 1.5 electron volts, which is very useful for application. Unfortunately, this material is unstable in air. So most people, experimentally anyway, when they study this sample, they would just cap it with substrate and a top layer. So for example, people have done an experiment to put black phosphorus on top of sapphire and then cap it with boron nitride layers. The assumptions are these are weakly interacting systems, so it shouldn't affect the property of the black phosphorus very much. But that's really not true. So here's our calculation for such a system for 1, 2, 3, 4 layers of black phosphorus. So these are isolated layers. These are the calculated quasi-particle gap, optical transition, and then the binding energy of the lowest energy exciton. For monolayer, binding energy is very large, 1.5 electron volt. Now, if you look at the experimental geometry of having a sapphire substrate and capping of boron nitride layers, then what you see is there's a huge change in the binding energy of the excitons. It almost goes to zero, and there's a big renormalization of the quasi-particle gap by around half a volt. Of course, for the thicker layer, this capping effect is not so important. So it really means that when you are looking at a cap one layer of black phosphorus, you're not looking at black phosphorus. It's just dramatically different. Now let me turn to a very new result and quite surprising result that we have got out on the dispersion of excitons in this material. Is looking at finite center mass momentum for excitons. We could solve the beta Saltini equation again from ab initio and look for this. And of course, so far we've been looking at the Q going to zero limit, which you could, which is relevant for optical absorption. For finite Q systems, you could also probe those in energy loss experiments, and those are very behavior at finite Q, of course, is very important to understand exciton dynamics and so on. And normally, you would expect the dispersion for the exciton as a function of center mass momentum Q would go like h bar Q squared with 2m, where m is the sum of the electron and hole mass. It turned out that's not the case for these systems. As I mentioned already, there are two valleys where the low energy states live in the precious metal carcinized. So when you look at excitons, if there's no interaction between the valleys, then you would just have two sets of excitons exactly of the same energy. However, the interaction, the electron-hole interaction, the exchange term, in fact, at finite Q, you do the analysis, mixes the excitons from the two volleys. In particular, it's due to this exchange interaction between the electron and hole. And so schematically, the Hamiltonian looks something like this. Is the for the light spin transitions, which are the optically active transitions, then the exchange term comes in, and you have the off-diagonal turns and mixes the two sets of excitons. For the unlight spin transition, which is typically sometimes called triplet, then those exchange terms will come in. And this is our ab initio result calculated for the dispersion near Q equals 0. So here, as I mentioned before, you have unlight spin transition and light spin transition is optically active. And I'm running out of battery. So you see that at finite Q, the two sets of degenerate excitons are now mixed and spread. And what's interesting is that you have this branch that has a linear dispersion relation. It's a massless like dispersion, and the velocity is about 1,000 times that of speed of light. And you could do analysis and obtain an effective Hamiltonian for the excitons. So if I use the basis as the excitons from the two bodies, and then determine a 2x2 Hamiltonian for such a system, then what you find is a Hamiltonian like this, where the intra-Wally, this is the exciton without at Q equals 0 energy, and this is the intra-Wally exchange term, and these are the inter-Wally exchange term. So you see the exchange term give rise to a non-analytic absolute value of Q term. And signals here are the polyspin matrices. And you could actually solve this Hamiltonian and get these two solutions. You have a lower band and the upper band. The upper band has this linear dispersion term, and the lower band has only the quadratic term. And if you think of the quantum phase between of the wave function of the mixing of the two volleys and coordinates a volley pseudo-spin, then this pseudo-spin actually has a winding number of 2, as I will illustrate for you now. So here are the results in more detail. This is the optically inactive state. This is the state one should be more interested in. And here is this pseudo-spins I talked about, so that for the upper band, it points in one direction, and the lower band points in another direction. It winds around twice when you go from here back to this point. As far as I know, this linear dispersion is the first time that I have ever seen about exciton dispersion in any material. And this result should be valid for any 2D system. And according to our calculation, you could actually see this effect through a simple experiment, absorptions experiment. So suppose you shine linear polarized light onto this sample and look at the absorbance of the light. Then what you will see is that the upper and lower band has a phase difference of 90 degrees in the absorbance as a function of the polarization angle with the linear light. And this is a direct consequence of the fact that the Wally quantum phase or pseudo-spin has a winding number Now let me talk about plasmons in this class of material. In particular, we're going to look at metallic monolayer transition metal dicarbogenized. They turn out to be also very, very interesting and different. So here's some earlier calculations on tantalum diselenide, which is metallic. And this is the calculated dispersion relation of the plasmon in the system. One expected for 2D metal, the plasmon should have a square root Q dependent. So this, if you use the density of carriers in tantalum diselenide, you should have a plasmon relation given by this dash curve. In the calculation, they cannot go to small q, so they could only calculate those points. So the data calculated points is significantly different from the classical dispersion, and it's not clear that it would actually ever follow the square root of q dependence. So we go back and we examine this problem, and we actually have to develop a new method to allow us to look at small q dependent, and this method allows us to sample around 400 million points in the Brion zone to get this result. And what you see is at high q, it agrees with the previous calculation, but at low q, it does have a square root of q dependence. But it's very far, once you have enough high Q, then it's very far from this classical 2D plasma. And the reason, in fact, after you think about it, it's quite simple. And that's because when you calculate the class of the plasma as a 2D metallic system, you are neglecting the screening of all the virtual interband transitions. So the real plasma dispersion should be really square root of Q divided by the dielectric function due to the interband transition in the system. As I mentioned before, the interband transition dielectric function, in fact, has a behavior like this, which have a strong peak at some distance. So that corresponds to a very large dielectric screening at some distance that will suppress the dielectric, the plasma dispersion. So instead of something look like square root of Q at sufficient Q, then it actually will suppress it because you are now reaching this regime of the screening. And this leads to the idea that we have of engineering 2D plasmons by putting appropriate dielectric material on the substrate, in particular IQ dielectric material. So let me just show you some results. These are just model results looking at tantalum diselenide and putting different putting it on different substrates. So you see that in isolation you have this green curve, but on different substrates you have very dramatically different curves. And this strongly illustrates how important substrate influence the property of 2D material. And this changes like 40%, right? People in plasmonics really have been looking at ways of changing both plasmon energy and group velocity and so on, which is a very good direction to explore. Now let me talk about some, I don't know how much time I have actually. All right. Some other interesting phenomena in other quasi 2D crystal. One is monolayer gallium selenide. This is again a layer material, but it has a structure different from that of transition metal dicarbogenized, and it has no transition metals in it. So its structure looks something like that, a single layer. And looking from top down, again you have a honeycomb structure. And its electronic band structure looks something like this. What's really interesting and curious is at the top of the valence band, it has a structure look like this. So you look at it in terms of energy versus Kx and Ky. In fact, it looks something like this, like a Mexican hat. And this thing actually exists over a very large part of K-space of the Brillouin zone. And that lead to a density state look like this. This is a total density state, and other the partial density states. So you see that that's a huge peak. And you look at the number, they're very large, larger than that of cobalt, iron, and so on. So whenever you have a big peak like this, you will think that if I could move the Fermi level here, then you're going to have instability and interesting cooperative phenomena, such as magnetism, superconductivity, and even good thermoelectric effects. And because you're in a 2D system, it's very easy to gate or load such a system by putting about 10 to the 13 or 10 to the 14 holes in the system. You could be in this peak. And this is the kind of doping you could easily do now experimentally for 2D material using ion gel techniques and so on. So that's what we're thinking about. We're exploring this region. Remember, these are all SP electrons. There are no D electrons in the system. And what we find is the system want to go to a ferromagnetic state, and it's due to a Stoner instability. So even with a very small doping, you will see that immediately it want to go to ferromagnet. And it has a moment about 1 Bohr magnetite per carrier. And when it's in such a phase, it's 100% spin polarized to one type, so it's actually a half metal. And a mean field calculation of the TC shows that this is, in fact, pretty high, it's around 90 degrees. And because this system has no inversion symmetry, the Berry curvature is actually non-zero for the system. So you might have interesting related Hall effects. In fact, Professor Wu's group has looked at whether you could look for this magnetism using optical probes, because this is only a one-layer material. But what they find indeed is that if you look at Kerr or Faraday effects, the rotation angles, in fact, is in the order of a fraction of a degree. So it should be quite easily seen in experiments. 5 minutes. Okay, maybe I could go through it. So another very interesting thing that we find is for black phosphorus. And it turns out that this system, we could make it such a way that you could switch the anisotropy of the photoconductivity and the transport of this material to a very interesting effect. A single layer of black phosphorus turned out to be highly anisotropic electronically that have been seen experimentally. For example, if you shine light along the x direction and look at the luminescence, it's very strong along the x direction. But if you shine light in the y direction, then the luminescence is completely suppressed. And you could see that also in transport experiments. So what we have looked at is not a single layer of black phosphorus, but a bilayer, but with the top layer that's twisted by 90 degrees, because we want to explore the anisotropy of between x and y. So here's the band structure for one layer, and then here's the band structure for the second, for the bilayer rotated by 90 degrees. So the Brion zone is this small region now because the two systems had to be made commensurate. What's really interesting is because the symmetry of the structure and the wave function, then the top of the valence band, there's no coupling between the top and bottom layer for those states. But for the bottom conduction band, there's strong hybridization. So the bands that are red is on the top layer, and the bands that's green, blue on the bottom layer. So that makes it quite interesting because if I apply an electric field perpendicular to the bilayer, then what you see is because of potential drop, it's not that much better. Because the potential drop here, you split the top of the valence band. And if I reverse the electric field, then you reversibly split the valence band. Now, the factor mass along along this direction is very low in this situation because of this, you're basically looking at this band, but very large along the x direction. But when you reverse the field, then you have the opposite occurring. So this is you can think of this as a field switchable transport and isotropy, and you could also have field switchable photochemistry in this material. It could be quite interesting to explore further the property of this material and possible applications. Now, finally, let me just mention one other interesting surprise that we got out from our exploration of 2D system. This is the phenomenon of what we call supercollimation of electron package in graphene when you apply a random 1D potential to the system, because normally you expect that random potential would just make things more diffuse. So the physics is basically due to the electronic structure. You have a kind of a direct cone physics here. There's a pseudo-spin associated with the electronic state, and it's because of this chirality of the wave function that suppress backscattering for the carriers in graphene and lead to interesting phenomena such as timing. So this physics lead to the following phenomena. If I apply a 1D disorder potential along the x direction, then the pristine graphene electronic structure, which look like this, actually transforms into a wedge-like structure because the suppression of backscattering. And if I form a wave packet within this wedge-like region, what we find is that the wave packet will propagate undistorted and guided to move along the x direction independent of original initial motion. So here's an illustration, a numerical illustration. You could get the other result, the previous results also from perturbation of the fourth order. So here is a realization of this 1D random potential, and we start a propagation of Gaussian wave packet in such a system. If you have a pristine graphene, this wave packet would spread as a function of time. It would look something like this as expected. But if you have this random potential, say along the x direction, then if you move the wave packet along the x direction, it stays a Gaussian wave packet, undistorted in this direction. And if you start the wave packet to move along some arbitrary direction, say 45 degrees, in pristine graphene it would look something like that. But in this one-dimensional fluctuating potential, in fact, it remains a Gaussian package and move guided in the x direction. So that's what we call supercalibration, but we have a quotation around it because there's actually a streak of reflected electron here, so it's not a complete transmission of the wave package. And this actually is fundamental to all direct cone physics. That is, if I look at surface states of topological insulator or certain photonic crystals, you would expect to see the same phenomenon. In fact, we have been collaborating with a colleague, a former student of mine, Chi-Ting Chen, at Hong Kong, looking at photonic crystals, and we see exactly the same phenomenon. This physics is related to the fact that you have no backscattering due to the fact that you have a pseudo-spin in the particle. So let me conclude, since I'm running out of time, and just give you some take-home messages. I hope I convince you that atomically thin 2D crystals are different. There's very strongly enhanced electron-electron interactions, and environmental screening is very important. That leads to a number of novel physics, huge exciton binding energy in photophysics, non-hydrogenic behavior, and even massless excitons. And then also you could tune the properties of the material, such as the transport, magnetic properties, and plasmonic properties, by using substrate and gating effects. So let me finally, this slide acknowledge my collaborators, all the work that I showed you I've done by my graduate students, and their work, their names are listed here, and these are my senior experimental collaborators who have been willing to look at our theoretical prediction and then doing some experiment on them. And thank you very much for your attention.
Okay, so there's a microphone in front of your seat, so yeah.
For gallium cyanide. For gallium